Es Hyman. Él es un matemático. Se graduó de doctor en matemáticas en la Universidad de Chicago, desde donde, luego de terminar su doctorado, se movió a la Universidad de Columbia, lugar en que trabajó hasta el año 1999, año en que se trasladó a la Universidad de Michigan, donde actualmente él está. Cuando salió de su doctorado, él perfectamente, o quizás alguien pensó que debía elegir irse a Princeton y dedicarse plenamente a la investigación. Sin embargo, él sintió que a lo largo de su carrera había tenido profesores, tan buenos profesores, que sintió que él tenía que enseñar también. Y por eso eligió la Universidad de Columbia. Su área de investigación es conocimientos disciplinarios y conocimientos para la enseñanza. El caso de la matemática.
My apologies for not speaking in Spanish. I hope you can follow my English. This is my second visit to Chile. I'm very happy to be here, especially at this very impressive Congress. My first visit in August of 1973 was during the last month of President Allende. Times now are also turbulent, but I hope with a much better prospect for the future. As you can see from the cover slide, what I speak about, it represents collective work with my colleague Deborah Ball, as well as a group of researchers over the past 12 to 15 years. My talk is very micro in contrast with the macro opening plenary from Professor Hargreaves, but it resonates very well with his notion of professional capital. So I want to speak about a particular aspect of human capital, what Hargreaves described as human capital, alongside of social capital, and I think it has some intersection with social capital. He explained that the interaction of professionals with each other actually contributes to their knowledge and growth, but the same applies inside of classrooms when you treat a classroom as an intellectual community in its own right, that you conceive of instruction not as a bilateral transaction between teacher and individual students, but rather as the growth of an intellectual community in which students are responsible for both understanding and critiquing the ideas of their peers. So this is about mathematical knowledge for teaching. The question applies to teaching any subject, and the premise is that to teach a subject, you must know the subject. That seems simple enough. This question has been around for many years, and interestingly, the natural, so to speak, answers to this have proven ineffective. Namely, the assumption was that to study the subject deeply in the academic tradition would produce more effective instruction. So we ask, what is enough mathematical knowledge to be an effective teacher? A major in mathematics is one possible answer. And at the pre-secondary level, majoring in mathematics is not associated with improved student learning. And even at the secondary level, the results of this are somewhat uneven. In fact, some research showed even, in some cases, a negative correlation between taking advanced mathematical courses and student learning gains. Negative correlation. So the message from that is not that deep subject matter knowledge is not relevant, but we have to refine and understand in a more sophisticated way what's behind the question. So we ask at first, how much math do teachers need to know, or what mathematics do teachers need to know and why? And we propose a somewhat different formulation of the question. Namely, what mathematical knowledge and skill is entailed by teaching? So note the shift from teachers, what teachers need, to what does teaching require? In other words, to understand this question, our approach was to analyze the work that teachers do and what are the mathematical demands of that work. So starting, our idea is rather than to look to the discipline or look to the curriculum, we look to records of practice. What do teachers actually do in their daily work, and what mathematical problems, what kinds of mathematical reasoning do they engage in the course of that work? So it's a kind of job analysis from a mathematical perspective. So once we understand what these mathematical tasks of teaching are, we want to then analyze this to understand what mathematical knowledge is entailed by that work. The result is a theory which itself is only a hypothesis. It's a practice-based hypothesis, and we would like to believe that this in fact produces better instruction and better student learning. So to do that, we have to find ways of measuring this knowledge. If we want to say higher levels of this knowledge produces higher levels of student achievement, we need to measure those two attributes to be able to compare them. So that has been part of the research program, and I will say something about the instruments developed to do that. And that has had positive outcomes. With that in place, then the question is, how do you create opportunities for our teachers to gain such knowledge? So the big clue is to understand that teaching mathematics is a particular specialized kind of mathematical work. Just like engineering, pharmacy, cooking, architecture, there are many professions which use mathematics in highly disciplined ways. Teaching is one of them, and when we prepare professionals in those other fields, we prepare them with mathematical knowledge that is adapted to the work that they do, and our proposal is that we should do the same with teaching. So I want to explain these ideas through a number of examples. Suppose you ask your students to explain what a rectangle is. That's a familiar object, and a student offers the definition. A rectangle is a flat shape. It has 4 square corners, and it's closed all the way around. So I'm speaking about levels in the upper primary grades, for example. What does the teacher need to know? Well, first of all, to see that something is missing in that definition, to decide what to do or say, and to offer a counterexample. For example, what kinds of shapes satisfy that definition but are not rectangles? So this has 4 non-straight sides, 4 right angles, 4 straight corners. Likewise, this one has more than 4, but the definition said it has 4, but nothing about exactly 4. So there are different nuances in the precision of the definition being formulated. So the posing of a mathematically correct definition that is at the same time accessible to young students poses a challenge for the teacher. So a possible response would be a rectangle is a flat shape with exactly 4 sides that are straight and connected end to end at square corners, and it is closed all the way around. Without the last sentence, you might imagine a plus sign, which has 4 right angles, 4 straight edges, etc. So this is one type of teacher work, trying to be precise with mathematical language and being attentive to nuances of detail. So teaching involves at least these three kinds of work: solving mathematical problems, engaging in specialized mathematical reasoning, and using mathematical language precisely but accessibly to the knowledge level of the students. So here's a further example of a problem-solving task. You want to know, you want children to understand how to put decimal numbers in order from smallest to largest. Okay, you want to propose a question that would test that knowledge. So you provide them with a list of decimal numbers and ask them to put them in order. Does it matter which list you choose? So here's one, here's another, and another. Which of these would be most appropriate to test student understanding of the order, putting decimal numbers in order? Which would you nominate? Or maybe they're all equally good. I have too many slides for this talk, so I'm not going to give you the time that I normally would to think about this. But one common error in student thinking about decimals is in their prior work with whole numbers, they ignore the decimal point. So you want to make sure that if you ignore the decimal point, that putting them in order on that basis would produce an incorrect answer. So example A suffers that shortcoming. Example B does even at a glance, because if you have the same number of places to the right of the decimal point, then the numbers treated as whole numbers without the decimal point would always have the consistent order. So part C would be the correct choice. Notice that the reasoning involved in this example was mathematical. It was not psychological or cognitive. It was not about pedagogy. It was a mathematical problem, and no one but teachers have to solve this kind of problem. They will not learn it in an academic mathematics course. Another is about using representations. Teachers may produce ways of representing mathematical ideas, or they may find them in textbooks, and the question is, are they really mathematically appropriate? Which might you choose to feature one or another aspect of the concept? So we want to find representations of division of fractions. This is one, another, another, and another. If you do the division numerically, you'll see that the answer is 2.5. And you can try to locate the numbers, the dividend, the divisor, and the quotient in each of these examples. Perhaps they're all appropriate representations of division of fractions. So again, if we had more time, I would let you reflect on this a little bit. The first one you see, the 0 to 1 is marked. We've marked off 3 copies of 1/3, and that passes the 5/6 halfway across the last third. So there are 2 1/2 1/3 in 5/6, which is one appropriate representation. The second one is another symbolic representation of the same idea. The lower right, you see the 2.5 as the answer, and one way to read the division is that 5/6 is 1/3 of something. And that something is 2.5 because you repeat 5/6 3 times. The one on the upper right is actually a representation of 5/6 times 1/3, not division, even though the numbers were chosen so that it appears that the correct answer, numerical answer showed up. This is a kind of mathematical thinking that teachers have to do. Analyzing errors. You teach children to do computations, constructions, and lo and behold, they don't always produce correct answers. What do you do when that happens? If you go to a doctor and he says you look sick, but knows nothing more than that, whether you need an aspirin or an appendectomy, you're not very helpful. So when a teacher sees a student error, they have to understand most errors are not accidental or clerical errors. They're the result of rational processes, and the teacher must have the capacity to diagnose what happened in order to know the appropriate intervention with the student. So here are 3 standard versions of a 2-digit multiplication problem. The correct answer is 1,225. So the teacher who knows how to do what she wants to teach the children to do can quickly recognize that these answers are wrong. But how did they arrive at these answers? Again, I won't have time to let you do the analysis. Let me at least ask, for example C, what do you think happened there? Where did the 1250 come from? Do you plan to teach 3rd grade, 4th grade? So the 1250 is 25 times 50, which is an easy multiplication, but then you have to compensate. There's a 25 adjustment, but unfortunately the student added instead of subtracted the 25. Example A is more subtle. So the 5 times 9 is 45. You carry the 4. And then instead of taking 5 times 4 and adding the carry, the student added the 2 4s to get 8 and multiplied 5 times 8 to get 40. Now that's a hypothesis that that's what the student was thinking, but you could actually test that hypothesis. Look what happened with the second line. 2 times 9 is 18, and then the carry of 1 was added to the 4 to get 2 times 5 to produce 10. Why would a student do this? Well, they've just learned the algorithm for addition, and when you add a column of numbers and carry, you can add the carry indifferently, and it doesn't affect the correctness of the answer. So it's a habit that would easily be transferred to multiplication. And so this is a rather subtle kind of analysis. Mathematicians do not know how to do this. So it's not a question of deep knowledge of the subject, but it's a question of specialized knowledge of mathematics that teachers need for their work. And there's little place in the standard curriculum, either in our methods courses or in our content courses, where they learn such things. What about correct answers? A correct answer may be arrived at either for the last one is what you might call, what's sometimes called partial products. If you think of 35 as 30 plus 5, and then 25 as 20 plus 5, then this is the standard binomial multiplication. Using language precisely. Here's a definition, or several definitions of even number, all of which arise in elementary classrooms. Are they appropriate? So the first two actually allow any number to be even. An even is any integer multiple of 2. That's actually a correct definition. And I emphasize when I say correct, these definitions are also accessible to children in the elementary grades. An even number is any number whose unit digit is 0, 2, 4, 6, or 8. So for example, 36.7 is an even number. A whole number is even if it's a sum of a whole number with itself, and that's actually a correct definition for children who have not yet seen integers and negative numbers. It's a correct definition of evenness for whole numbers, and it's consistent with the definition of evenness for integers, which will come later. So again, teachers have to know how to anticipate what's coming mathematically and not say things that have to be betrayed later. For example, that you cannot take a large number from a small number. Posing mathematical problems. So again, the way a task is formulated can have a great deal of bearing on the mathematical work that children have to do and what the learning goals are. So by the way, these coins, which are American coins, have these translations. So there are different kinds of wordings that you could propose and that have different instructional outcomes. So one is example 1 is the task as described. Number 2, just ask for combinations of coins. It doesn't involve the arithmetic of the coin values in tabulating the results. And the third adds a task of proving that you have found all solutions. So children could generally quickly, in a reasonable amount of time, generate all of the possibilities, but asking that they actually prove that there are no others is a much more sophisticated and cognitively demanding task. So these 3 versions have very substantial differences in the kind of mathematical activity called for. So again, with rectangles, suppose you were teaching the concept of rectangle. This is a task of instructional design. In what sequence would you introduce a set of examples like this to introduce them to the concept? The idea being that you want to give them not only examples, but also non-examples to find exactly what the contours of the concept are. Some children have called example E a parallelogram because they were told that a parallelogram is a tilted rectangle. So again, I repeat that teaching involves special kinds of mathematical work, solving problems, engaging in special kinds of mathematical reasoning, and using mathematical language precisely and accessibly. So here are examples of each of these. So selecting or constructing a strategic example, representation, or task, analyzing representations, definitions, non-standard correct responses, incorrect responses, and developing and using appropriate language. Sorry. So here's an example with specialized reasoning. We just looked at the example of starting points and sequences in introducing a concept. These are features of using mathematical language precisely but accessibly, and taking into account differences in the home language of students. Of course, in the United States, we have an extremely diverse population with many children speaking a different language at home, and even those who are normal English speakers have a very different common language outside of school, and technical language that is introduced when they're studying mathematics. So what makes this kind of work special for teaching is that it's knowledge performed in the service of helping others learn mathematics, and its warrants are tied to both pedagogical purpose and to mathematical integrity. So what kind of mathematical resources are needed to engage in these special kinds of work? We've developed a theory about this called, this kind of knowledge, which we call mathematical knowledge for teaching. And it builds on the tradition of pedagogical content knowledge introduced by Lee Shulman back in the 1980s. Shulman distinguished various kinds of knowledge that were important for teaching and tried to emphasize that, or resurrect in the concept of teacher knowledge the important role of content itself. And he identified as pedagogical content knowledge a kind of knowledge of both the discipline and of aspects of pedagogy, knowledge about student thinking, common student errors, etc., and also knowledge that combine mathematics and knowledge about design of instruction. For example, instructional sequences, etc. He left content knowledge as a kind of undifferentiated block, and much of what we have done is to more finely distinguish domains within subject matter knowledge. So the schematic with which we represent these ideas looks, we call this, it's sometimes called the egg. So on the pedagogical content knowledge side, we have knowledge of content and students, for example, common student errors, knowledge of content and teaching, instructional design, for example, and knowledge of content and the curriculum. And on the subject matter side, we have what we call common content knowledge, specialized content knowledge, which I've given you some examples of already, and then something we call horizon content knowledge. Now, common content knowledge is, it may be an unfortunate choice of terms. It's not necessarily very common in the sense that the typical person on the street will know this kind of mathematics, but it's common in the sense that it's a knowledge of mathematics that's held in common with other professional users of mathematics. So there may be knowledge that mathematicians or engineers or pharmacists or other users of mathematics have that teachers also need. But the specialized, which I think is one of the more interesting categories that we've identified, is knowledge. It's special in the sense that it's required by teachers, but not apparently for other users of mathematics. And the very existence, when I tell mathematicians about that idea, they often challenge me to give an example of a kind of knowledge of mathematics that teachers would need that they don't already know. So I give them examples like I just showed you. So if we look, for example, at the concept of a rectangle, here's how that concept traverses this egg. So on the common content side, it would be a task like draw a rectangle. That's common content knowledge. Specialized would be which of these figures is good to assess whether students understand what a rectangle is and why. That's a kind of specialized knowledge about rectangles. Which of these is a mathematically appropriate, accurate definition of a rectangle? So again, this is specialized knowledge. All of these definitions look at first reasonable. So with the first one, it suffers from the common misconception among students that a square is not a rectangle. The second one A rectangle is a shape with exactly 4 connected straight line segments meeting at right angles. That sort of looks like a rectangle. A rectangle is flat and has 4 straight line segments, 4 straight corners, square corners, and it's closed all the way around. So this one is because it's not exactly 4, but so this attention to precision of language, again, in the case of rectangles, shows up in this way. Here's something about knowledge of content and students. So we're on the pedagogical content knowledge side. Write a mathematically accurate definition of rectangle that's usable by 2nd graders. So this is a mathematical question, but it involves knowledge of students as well. How can the notion of simple closed curve, which goes into a mathematical definition of a polygon, for example, be expressed in a way that's both mathematically accurate and usable? And which part of this phrase is most challenging for children? So these are examples of combination of mathematics, knowledge of mathematics, and knowledge of students. What are children likely to know about what a rectangle is? What do students typically have difficulty with in learning about rectangles, and why? Knowledge about teaching and content, teaching in mathematics. How would you sequence, this is a question I presented to you earlier, how would you sequence these figures to discuss the concept of rectangle? And what task would you create using these figures or others to set up a productive discussion aimed at developing a definition? So notice the premise behind this is not that definitions, formal definitions, are given to children, but they are developed collectively through student discussion of the idea. Horizon content knowledge, well, we're not too attentive to the distinction between a rectangle as a one-dimensional perimeter versus rectangle as an area, as a region of the plane. So, but nonetheless, both of those ideas are important. If you introduce the shaded version, it's a distinct idea, and it's important to recognize that it is distinct mathematically. Another piece of horizon knowledge is that rectangular areas will in fact be the building blocks for the general concept of area later on, which is actually a rather subtle notion. So what mathematical knowledge for teaching is it's not just knowing the topics of the school curriculum. It's not just knowing school content from an advanced perspective. It's not just another term for pedagogical content knowledge. And it's not being able to teach the content. What it is knowing mathematics from the perspective of helping others learn it, and being mathematically ready to teach an idea, a process, or other aspect of mathematics. So here's another sequence traveling through the egg, this time division of fractions. So this is our friend 5/6 divided by 1/3. The common knowledge associated with this would be calculate that division. Here's a piece of specialized knowledge. Someone replaces the two fractions by equivalent fractions with the common denominator, and then produces the answer by simply dividing the numerators once the denominators are common. It produces the correct answer. A teacher has to know whether or not that procedure is legitimate mathematically. Specialized knowledge, which of these examples appropriately represents this division 5/6 divided by 1/3. Knowledge of content in students. Here are some things about what are common errors that students make when dividing fractions, what student experiences with division of whole numbers supports their understanding of division of fractions, etc. And knowledge of teaching and content, which representations would you use to introduce the meaning of division of fraction or explain the invert and multiply algorithm? What sequence of problems would you use to begin work on division of fractions, etc.? And for horizon knowledge, a student comments that if you divide by smaller and smaller fractions, the answers get bigger and bigger. Is the student right? And is this mathematically significant or interesting? Well, it is mathematically significant and interesting, and a teacher should recognize that the student is not out of place in calling attention to that. Division of fractions is a case of division of real numbers, and similarly for all of the basic arithmetic operations. Part of horizon knowledge is to understand that the various systems of numbers, whole numbers, integers, fractions, are not living on different planets, but ultimately they all have a home on the real number line with a coherent set of operations, arithmetic operations, obeying the basic rules of arithmetic. So that's an ultimate conceptual image of where all of this is going. Teachers should be aware of that destination and not do things to compromise that trajectory. Knowledge of content and curriculum. At what grade levels are students taught to divide fractions? How is division of fractions related to division of whole numbers in the school curriculum, etc.? So that's a brief survey of the theory of MKT, mathematical knowledge for teaching. Why is it a good theory? Why, on what basis can we warrant that it's good for teachers to know mathematics, this kind of mathematics in this kind of way? So in mathematics, we warrant claims by providing deductive proofs. Education is a very complex social science, at least from the point of view of research. So what could warrant a claim about mathematics that teachers should know? Opinion, that's what we've relied on for a good part of our history. Professional judgment, likewise. The content of the school curriculum, that has some relevance. And evidence about the connection to mathematical quality of teaching and to student learning. So our argument is that it's appropriate to seek warrants based on the last two criteria. And how do we do this? So we do empirical testing and improvement of the theory of mathematical knowledge for teaching by, first of all, developing measures of this, doing factor analysis and validation studies to distinguish the various domains of this kind of knowledge, developing the theory, and the measures are needed in order to, we want to compare mathematical knowledge for teaching with quality of instruction and student learning gains. And in each case, in order to do that, we need to be able to measure mathematical knowledge for teaching, use some sort of observational measures of the mathematical quality of instruction, and third, some measures, and in this case we use standard tests for student learning gains. So what I'm showing you now are some examples of items that are on our measures. Okay. For the work that we did, it was important to administer these measures at scale, which required, for pragmatic purposes, that we do it with multiple choice questions. It was not at all clear a priori that you could measure this kind of knowledge, which is somewhat subtle, in multiple choice formats. So it was a challenge to actually accomplish this. So one type of item is to present teachers with this kind of example and ask them to analyze the errors that were involved. Here's an example which I like. Student performs the subtraction problem of decimals, 3.6 minus 8.2. So the 6 minus 2 gives you 4, the 3 minus 8 gives you -5, so the answer is minus 5.4. Okay? So how do you assess this? Jose is correct, Jose is wrong, Jose has used an inappropriate method, or Jose's method is correct, but our notational conventions lead to a misreading of the answer. What answer do you choose? This is one where you can sort of use test-taking skills to realize that the complexity of D is probably the right one. So the correct answer, Jose arrived at the correct answer, which is -5 plus 0.4. But the notation leads us to read this as -5.4. So what Jose did was mathematically correct. And it's easy to imagine him doing this, but what does the teacher need to know in order to analyze such an outcome? So I'll have to rush through these other items because we're almost out of time, but there are various examples of items that show the nature of the measures that we use for MKT. And then we use data to test and improve the theory. The validation of these measures was interesting. First of all, how do we know that correct teacher answers on these items reflected the appropriate thinking? Well, we did cognitive interviews with the teachers to try to understand why they gave the answers that they did. And these were generally positively correlated. To see whether high MKT scores corresponded with what we call high mathematical quality of instruction, we had to develop observational codes for looking at instruction, video and otherwise, and use these codes to independently measure what we call mathematical quality of instruction. And again, there was a high correlation with high scores on MKT. The scores reflect common and specialized content knowledge. So we gave these items to research mathematicians, many of them quite distinguished. You would expect people with deep knowledge of mathematics to do well on these, and in fact, they did well, most of them, just by the sheer magnitude of their mathematical knowledge they could get through, but they were not able to answer all of them well. Some of them saw these numbers and these computations that where on earth did the student come up with these numbers? And finally, most importantly, higher scores related to student improvement. This was a very large-scale study in high-poverty urban schools, and even though the effect size is small, as you would always expect from an intervention of that kind, there are many factors that affect student outcomes. The effect size was comparable with socioeconomic status, which is considered to be the highest predictor of student success. So that was quite significant. Here's just a quick picture of mathematicians' performance on our items, and you see that they're all pretty successful, with a few interesting exceptions. So some of the items were challenging to mathematicians, which again emphasizes the special nature of this kind of knowledge. So there are easily explained reasons why some of these items challenged the mathematicians. Some of them were flaws in the items themselves. Some of this work has been done internationally. The measures have been applied in Norway, Ireland, Indonesia, Ghana, and Singapore. So the final question is, how can you create opportunities for teachers to learn this kind of mathematical knowledge? And I think we've run out of time, so I won't try to go through those slides now. Thank you for your attention.
Si tuviéramos un país imaginario, no aquí en Chile, nosotros tenemos en este país escasez de profesores especializados en matemática, en educación elemental. ¿Qué sería más fácil o cuál sería la solución? ¿Capacitar a ingenieros o capacitar a profesores sin especialización? Esa es la primera pregunta. La segunda pregunta, usted ha estado abordando en su ponencia cómo los niños elaboran algoritmos o estrategias, pero usted ha incursionado en el área de que ellos puedan crear problemas o crear situaciones problemáticas.
Could you repeat the second question?
La segunda pregunta, que me dio la impresión de que la ponencia usted abordó más bien de cómo los niños enfrentan los algoritmos o cómo enfrentan metodológicamente una problemática. En su experiencia profesional como docente, ¿ha incursionado en el área de tener una fórmula de cómo enseñar a crear situaciones problemáticas?
Should I answer now? Did someone want to say something further? Okay. So when you say teach engineers or professors, are you using professors in the way Chileans do, meaning school teachers, or do you mean university professors? School teachers. Is it easier to teach engineers or professors? Is that your question? It's probably easier to teach engineers. So we have a great problem in the United States with improving what Professor Hargreaves called professional capacity, human capacity. And what I spoke about is one component of that. Generally, the efforts to reform education in the United States have addressed the problem through curriculum. Teacher capacity is a problem of transforming almost 4 million human beings. It is the largest profession in the United States, and that is a matter of decades of work, at least a generation of work. So we are very far from knowing how to do this. Even if we had the resources and the public and political commitment, we don't fully understand the best way to prepare teachers. And what I spoke about is only a beginning piece of that question. So the question of preparing teachers is vastly more complicated and difficult than training engineers, which we do know how to do. The second question, do we know how to create problematic situations in the teaching of algorithms? Yes, we do. And these ideas are not specific to the United States. Other educators in Holland, in France, and Germany have developed very good ideas about instructional tasks. In common with the Japanese, we tend to lead students toward error because error is a major site of learning of mathematical concepts. But strangely, we have a culture in the United States where teachers feel that errors are like bacteria and the classroom should be purged of them as soon as they appear, and are fearful of trying to manage a class or their students being contaminated by wrong mathematical thinking. So there are known ways to intervene on this, but it's not a common part of teacher professional knowledge or capacity.
¿Tomamos otra pregunta? Última pregunta, y cortita. Cortita.
Trataré de hacerla cortita, pero es importante. Lo que pasa es que el problema es el lenguaje matemático. Hoy los niños tienen dificultades para aprender matemáticas porque no razonan matemáticamente, no piensan matemáticamente. Pensar matemáticamente es distinto a pensar verbalmente.
De verdad que necesito que hagas la pregunta, porque me dijeron que...
Es importante. Entonces la pregunta es cómo profesores que se han formado sin necesariamente este pensamiento matemática, ¿cómo le enseñan a niños a razonar matemáticamente? Hoy día los niños aprenden las tablas de multiplicar de memoria. ¿Cómo enseñar a pensar matemáticamente?
Teachers who have not learned how to reason cannot teach children how to reason. So learning how to think mathematically and to reason mathematically must be a part of teacher education and professional development. And this is very much a part of our thinking about what teachers need. So we can't expect children to prove theorems in the sense that mathematicians do, but developing the need for explaining mathematical ideas, for example, in the coin problem, asking them to justify that they have all of the solutions to that problem is an incipient form of a mathematical proof task. They have to organize the space of solutions, find some structure in it on which they can rest an argument that shows that they have exhausted all the possibilities. So there are ways to design tasks that call for children's reasoning, but teachers in turn must know how to both design and use such tasks and how to orchestrate a discussion among the students to carry that out.
Bien, agradezcamos nuevamente al profesor Hyman por su excelente...